All right, here we go with the next chapter here. We're going to talk curve sketching. We're going to make some crazy graphs. This chapter is pretty cool. And we're going to start off with extreme values to help us do that. So when I think of extreme, I think of the awesome rock band from the 90s. And maybe you're familiar with their famous song, More Than Words. Classic love song. Even if you don't love songs, you're probably going to love that love song. I'm going to play at the end for you. Let's do some math right now. So let's talk Extrema. What are Extrema? When we're looking at these graphs, we need max and minimum points. So these are called our Extrema. So we have max and minimum points. And we're going to throw a lot of vocab out here. So a couple of different types. We have the absolute max, the highest it'll ever get. We have the absolute minimum. So this is the highest and lowest the graph ever gets. Then we have, within a little interval, we have a local max and a local minimum right there. Alright, so let's check out this graph. I made this crazy looking graph over here, and let's label these parts to this graph. So if you're following this along, we've got an increasing function, then it changes to a decreasing function. That's what's going to cause these extrema, when you go from increasing to decreasing or from decreasing to increasing. So this right here is a maximum point, looks like a maximum point, and in fact, it is the highest point possible, so that is an absolute maximum. So that is the highest possible point that we can have on this function. So this point right here, we're going to say is our absolute maximum. Awesome. Moving on, if I follow this down then up, I've got a minimum point, but this is going to be a local one. So this one here is local because it's happening just within the interval. It's not the absolute lowest point, but it is a pretty small point. You can see we're going to have another max, another min. If my pen works, there we go, and then another max up here. So let's make sure we label this. This next max here is got to be a local because he's not the highest point, so he's the local one, and we'll make him a little smaller. Not that he's less important, but just because he'll fit in there. Okay, so that is a local max. And then we've got, is this the absolute? No, it's still another local min. So you can have multiple locals, but you can only have one absolute max or one absolute minimum. Then what happens here, this point right here is sharp, it's a cusp, it's pointy. Pointies don't have derivatives, but it's still a maximum, isn't it? In fact, it's going to be a local max right there, and I'm going to shrink him down too. And then what is the finale here? Well, this goes to infinity negatively, negative infinity over here. I don't have an absolute min. So you don't have to have all of them, you can have bits and pieces of them. Awesome. So a couple things to know is some more vocab. Absolute max, you may see this referred to as a global. Think worldwide. The biggest max, you could have a global max or a global min. That's the same thing as absolute. And sometimes we refer to local as relative. It's relative to the domain, not like your aunt or something. It's relative to that domain. So that's some more terminology. You may see this. I may throw it out there every now and then, but really we're going to use absolute and local. Boom and boom. Awesome. So what we're going to do is we're going to find what's called critical points. These are critical points. What are critical points? Let's jot this down. It's when the derivative is 0 or the derivative is undefined. So check it out. If we come back up to our picture, yeah, the slope of the tangent line here is 0, definitely. The slope of the tangent line here is 0, slope of the tangent line is 0, slope of the tangent line is 0. This causing these max and min points. Whoa, what's the slope of the tangent line here? Doesn't exist. It's pointy. It doesn't have a derivative. So these are the critical points. Some things, some critical things, I suppose, are happening there. So we're gonna find out when it's the slope of the tangent line is 0 or undefined. Awesome. That's the whole section. Let's break it down into looking just on some different domains here. So I got a parabola. This is just like an x squared type of thing. I shifted it over, but what do I have in a parabola? Well, in the normal positive parabola, you have an absolute minimum. So you're going to have your absolute minimum right there. What happens when I change the domain, though? So check this out. I'm going from 2 inclusive to infinity. What does this do? Well, I still have that absolute min. It never gets smaller than that. But what does this little dot over here do? This is going to give me a local max. It's not the highest possible point. It's not the absolute, but it is a high point right there. Awesome. So I go over the next one. We already said that was a local max. Then what happens? We had that absolute min. He's still an absolute min. Then I come up and notice it's non-inclusive on the 5. I don't include that. It's an open circle. So what is that? It's nothing. You'd like to say, oh yeah, it's going to be the absolute max, but it's approaching this y value of 5. It never makes it. It's like 4.99999999999. Never makes it, so it's not a max. It's not a point. That is all this one has. So I'm going to limit it down to these domains, and that's what happens on these different domains. Awesome. How about some new graphs? So I kind of took like a cubic function here. So let's check it out. This is the absolute lowest point possible. So we've got an absolute min right here. And what else do we got? At this point right here, I can tell it's a slope of 0, so that's going to be a local max. So I'm going to have a local max right here. Then what else do we got? Looks like a local min. Drag this bad boy in here. And then now, since that's a solid dot and the highest, we have an absolute max right there. So if you want to see the points, this y value here, we're always looking for the y values for the max and mins, and that's the lowest point right there. Excellent. So what happens when I change my domain? This was inclusive. Now one side is not inclusive. What do I have here? Nothingness. What is the rest of this? Well, the rest of this is still the same. I still have that local max. I still have that local min. And I still have an absolute max up here. Love it. Love it. Now I cut same cubic function here, but I cut the domain off instead of at 6, at 5. What happens? I know open dots are nothing. They're always nothing. What happens now to this? This actually is higher than that one, so we actually have an absolute max now. So you can see by changing the endpoints, it definitely changes what's happening at these critical points. I still have a local min here, and now this becomes a local max. It's not the highest here at the end. The other one beat it out here. This one is actually higher, so it's the absolute. So pretty cool. So if we change the interval, it's definitely going to change how these things label. Some other weird things here that can happen. Remember, I've been looking at these critical points as when the slope of the tangent line is 0. But here are the weird one. What's the slope of the tangent line here? So this is actually a critical point right here. When I've got this transition, this is probably a cube root function. The slope of the tangent line here is what? Oh, it's vertical. So it's undefined. That has no slope. So this is still a critical point. We would say there's a critical point when x is 3. That is definitely a critical point. But is it a max or min? No, it's not. In this case, it is not. Pretty interesting. So right here, we're just going to call this a critical point. So do you see critical points? Yeah, I got this max. This min right here is also a critical point. Is it, in this case, any kind of max or min? Sure it is. So this is a local min. What is this bad boy up here? It looks like we got an absolute max at the top of this thing. What else do we got? I think we got an absolute min down here. And what's the last thing? It is nothing. So these are the critical points in here. And this actually, even though it has no derivative, it's an undefined derivative, it is still creating a minimum point. So sometimes they will, sometimes they won't. Awesome. How about this case over here? So I can see I've got a critical point here when x is 2. So when x is 2, something is going on over here. It's this point right here. What's the slope of the tangent line at this point? We'll check it out. Womp. It's 0. Isn't it? The slope of the tangent line is flat. It's 0. Is it causing a max or a min? No, it's not. It's actually going to be called a point of inflection later on, but for now we're just going to refer to it. It is a critical point. It's not a max or min. So what do I got in this case? I do have an absolute max and I have an absolute min. Woo! Cruising along. That's a lot of info right there. Alright, so if you check out the bottom screen here, this is the extreme value theorem. So we don't really use this much as like the mean value theorem or the intermediate value theorem, but the extreme value just says when we have these closed intervals here, so if you're continuous on a closed interval, like this middle picture here, continuous on a closed interval, then you have to have both a maximum and a minimum on that interval. So, I'm sorry, that one's not closed. Dang it. Alright, so we got the extreme value theorem here down here at the bottom. It's not like we don't use as much as like the mean value theorem or the intermediate value theorem, but the extreme value theorem says what? If you have a function that's continuous in a closed interval, so like this last picture here, I've got this closed domain here, this interval from 1 to 3 inclusive. When you include a and b and it's continuous, you got to have a max or a min. That's just how it is. That's what the theorem says, and it makes sense. You're in this closed interval, you're either going in continuous, you're going to have a high and a low point. So you'll have to have a max and a min on the closed interval. Hopefully you're good to go. Let's put this into action. So without the graph, so I wanted to really visually see it. Let's actually just do it. We're going to find the critical points. So if we're finding the critical points, we're looking at what? Critical points have to do with the derivative. So find the derivative. So do a little power rule here. This will be what? 1/3 times 3. Drop the power 1. We got this. And what am I going to do? I'm going to set it equal to 0. This is how I get critical points. Or I'm going to see where is it undefined. Well, this is a parabola, it's never undefined, so I don't have to worry about that. What does this factor down into? It looks like it's special case, difference of squares, x plus 3, x minus 3. So where are my critical points? My critical points, if I solve this, would be when x is negative 3 or positive 3. These are my critical points. Now later on in the chapter, we're going to find out are they max or mins or inflections. But right now, we're just going to say, hey, Those are critical points. They're important to me. They're critical. Awesome. Let's come over to this bad boy over here. We're going to do the same thing. Let's find the derivative. So I'm going to rewrite this. That kind of looks crazy. So really this is what? This is the square root of 4 minus x squared. And it's to the negative 1/2. So rewrite this bad boy. Now let's derivatate. Can you derivatate? I don't think that's a real thing. Let's take the derivative of this. So we're going to say g prime is going to be negative 1/2. And then we've got this 4 minus x squared in here. And drop that power to negative 3/2. And don't forget we're chaining rule in this. So what's the derivative of the inside? We kind of froze the inside. What's the derivative of the inside? It's negative 2x. Fantastic. Man, my handwriting is killer. Killing it tonight. Can we clean this up a little bit? So I'm going to set the derivative equal to 0. This 1/2 will cancel this 2. The negative and the negative really makes a positive. So I'm really looking at what? X over, holy cow, what is this? This is the square root of 4 minus x squared cubed. Oh my goodness, that's pretty rough looking. So when this happens, this is a great example right here. This is great. So two things. I'm looking for when is the derivative equal to 0. So when I have a fraction here, a rational equation, I only care about the top. When does the top equal 0? So when does the top equal 0? Well, there it is, x equals 0. So that is 1. That is a critical point for me. That's a critical point. And I can't divide by 0, so you have to come down here to the bottom and you have to say, when does this hot mess, 4 minus x squared cubed, when that is not allowed to equal 0. If it does, you're dividing by 0, it's undefined. So you can solve this one, I hope. You can go through the math, but maybe you can just see it. Like, if I'm just going to tell you the answer. I can look at this and say, hey, when will this be 0? Well, when x is 2 plus or minus 2, isn't it? Because if 2 squared is 4, negative 2 squared is also 4. But if you want to go through the math, you can square both sides, and then you're left with 4 minus x squared cubed. And what's cool about this, when you square cube things, if I cube root this, I'm still at 0. So the cube root will cancel that cube root, and you're left with this 4 minus x squared equals 0, and then you can factor that and solve that. But that's the key right there. These are my critical values. So when it equals 0, if I have a fraction, I always got to set that denominator equals 0. That's undefined. So critical point. Boom. Cruising. What's next on this? Let's take it a step farther. So now I actually want to label these. I'm going to find the critical points, and now I'm going to tell you what they are. Are they going to be maximums or minimum values? So a little bit farther, and we're going to do it on an interval. The last one there was no interval. If you think back, I just said find them. Now I only care about them on this interval. So let's do this. So the first thing I'm going to do, that looked terrible. I was just saying how good my handwriting was, and I blew it. We're going to find the derivative. So let's find the derivative of this bad boy. I've got 3x squared minus 6x. The 1 disappears. And I'm only interested about when does this equal 0. So I'm cool, there's no fraction, so I don't have to worry about undefinedness. I just have to worry about when does this happen. So again, another factor. In this case, they both share a 3x, so I'm going to undistribute that 3x, and I'm left with x minus 2. And now I should get two answers here. What makes this parentheses 0? What makes this 0? So when x equals 0 is one answer, or when x is 2. So that makes this 0, that makes this 0. Those are some great arrows. Awesome. So these are my critical points. That's great, but we have to do a little more work than this. So when I'm checking this graph, I'm only caring about this interval. So I don't know, are these max or mins? I don't know if they're the highest or lowest. So I actually have to go and plug them in. So I have to check the point. So the first point I have to check is the left endpoint. What is the f of negative 1/2? Then I'm going to check the f of 0. That's my critical point. Then I'm going to check my next critical point of 2, and then I'm going to check the right endpoint of 4. You have to check all 4 of these points because something critical is happening right here at 0 and 2. And then remember, the endpoints can also be the absolute min or max. If you think back to our pictures, so I got to check all 4. So we got to plug these bad boys in there. So we have to actually find, and I'll write it down here, the f. Let's change colors here. We got a lot of action going on here. Let's change this up. What is the f of negative 1/2? Well, I got to plug negative 1/2 into my function. I have to say negative 1/2 cubed minus 3 times 1/2, negative 1/2 squared plus 1. So it's kind of a pain. This fraction makes this one a little bit tedious, but I can cube 1/2. 1/2 times 1/2 times 1/2 is negative 1/8. And then if I square it, I get 1/4. I got which becomes positive though, so it'll be 1/4 times that by 3, it'll be 3/4. and then I'm going to add 1. So if we clean up this fraction here, oh my goodness, I can make this all minus 1/8. Let's turn this into 8, so that'll be minus 6/8. Let's turn him into 8s, that'll be 8/8. So if you get a common denominator, what do I get here? It looks like I get minus 7/8 plus 8/8 should equal 1/8 as my value right here. Holy cow, that was a pain. Usually they're not that bad. In fact, 0 is super easy. Plug 0 here, the f of 0 is easy. 0 cubed minus 3 times 0 is easy. You're just going to get 1 here. So that one's great. How about 2? If I plug 2 in there, 2 cubed is 8. I'm going to go fast here. I hope that's okay. And then I'm going to go minus 3 times 2 squared plus that 1. So 8 minus, I think that's 12, plus 1. So 8 minus 12 is negative 4, plus 1, that looks like negative 3. Whoa, handwriting. Let's try it again. There, that's a good looking 3. And then let's do the last one, 4. 4, maybe I'll jot down here. We got a little bit of room on this page. So if you're finding the f of 4, you're going to say it's 4 cubed minus 3 times 4 squared plus that 1. So big plug and chug right here. It looks like 4 times 4 is 16 times 4 is 64. And I'm going to say 3 times 16 is 48. I hope that's right. And I'm going to say plus the 1 at the end. So 64 minus 48 is what? 16 plus that 1 is 17. So what do I have going on here? Who's the biggest point? Well, 17 is the biggest. So this guy right here is my absolute maximum. So I'm going to say that is my absolute maximum. What is my lowest point? Looks like negative 3. So he is my absolute minimum. So absolute minimum, this guy is the absolute minimum right there. So you have to find all these values here, test all the endpoints, the critical points and the 2 endpoints, and then the lowest one's the absolute minimum, the highest is the absolute maximum. So I'm going to move him out of the way so we can do the next problem here. Let's just kind of squeeze him, maybe shrink him down. There we go, like that. Awesome. So let's check this out. I'm going to put a little calculator symbol here every now and then because sometimes the numbers get a little hard to crunch, and I don't want you, don't cheat and graph it and look, but I want you, if you need to crunch the numbers, to compare who's bigger and smaller. If you want to try this work ahead of me, that's cool, but I'm going to go step by step and do this one because I want to make sure we're cool on this. So let's find all the critical points on this one. So I'm really looking at what is the derivative. What is the derivative of this? So it looks like the derivative of 2x is 2. If I bring this down, I'm going to say 2/3 times 3 is 2x. Drop that power to what? The negative 1/3. So I'm looking at this. Then I set the derivative equal to 0. So I've got 2 minus, let's rewrite this. So it's 2 over x, the cube root of this bad boy right here. So I got this thing going on. So right here, so I got to solve this. Before I solve it, we've got a fraction. So remember these excluded value things. We have to think of the excluded value. So this is a trouble for me. This is not allowed to be 0. So the cube root of x is not allowed to equal 0. If it did, it would be undefined. So that actually is a critical point. So the cube root of what number is 0? Well, it's just 0. I mean, you can cube both sides, but really x is not allowed to be 0. So this is a critical point. So x equals 0, critical point. What else is critical? Well, now we got to go back and solve this thing. So maybe we can get this out of the way so we can solve this bad boy. In fact, I'm going to move this whole thing out of the way. We got a lot of, this is a big problem right here. So I'm going to move him over here. There we go. And let's solve this now. So we're going to say, all right, how do I get x by itself? Well, you can subtract these 2 from both sides. So you're looking at negative 2 equals negative 2 over the cube root of x. Whoops, I put the wrong thing in there. Whoa! Alright, so that would be negative 2. Those cancel, and I'm looking at negative 2 over the cube root of x. So this is kind of weird. What do we do next? Well, I hate to have variables in the denominator, so I'm going to multiply both sides by the cube root of x. Whatever you do to one side, you got to do the other. And that's good because that'll cancel out this, that'll cancel out this, and this is the whole times thing. So I'm really looking at negative 2 times the cube root of x equals negative 2. Well, that's good because I want to get x by itself. So what am I going to do? Just divide by negative 2. So kind of some weird algebra here, but don't freak out. I'm going to end up getting the cube root of x equals 1. And again, you probably do have what number if you take the cube root of it is 1? Well, it's just 1. But if you want to do the math, you are going to get rid of a cube root, you just cube both sides. So that's really 1 cubed, which is 1. So here are my two critical points. X equals 1 and x equals 0. So, all right, so I got the two critical points. So what do I got to do now? Well, I have to see who the biggest and the smallest is. So I got to check the endpoints. So remember, this is the h of x. So this I'm going to find the h of negative 1. And then I got to find the first critical point is 0. What is the h of 0? Then I got to find the h of 1, the other critical point. And I got to check the right-hand interval, the h of 3. So I'm got to just see who the biggest and smallest are. I got to find all these points here. So when I put negative 1 in here, what is the h of negative 1? Well, it's 2 times negative 1. And maybe you want to rewrite this. I don't know. It's 3 times, remember that's the cube root of x squared, and x in this case is negative 1. Holy cow. Hopefully I got some easy numbers here because 1's great. I square negative 1, I get 1. You cube root 1, you get 1. So really that's just minus 3. So it should be negative 2 minus 3 should be negative 5 when I plug that in there. I love plugging 0, and I'll plug 0 in all day because what happens here is 0 minus 0. That is just 0. Plug 1 in here. Well, you know, 1 to any power is 1. So it's still going to be just this minus 3 idea here. This is 2 times 1, which is just 2. 2 minus 3, negative 1. And this one looks like the weird one here. Maybe I need to actually write this one out. So if I do the h of 3, that's going to be 2 times 3. And that's going to be minus the cube root of what? 3 squared. This doesn't look like it's going to end well for me. So the 2 times 3 I got, no problem. That's going to be 6. But what is this? Well, 3 to the... I can square that 3 and make it 9, but that's not friendly, is it? The cube root of 9, it doesn't work out friendly. So that's what I was saying. Hey, man, let's get our calculator, throw it in the calculator, and see what it says. So I'll put it over on this side so we can see. So what is that actual decimal? So we can type it all in. We can say it's 6 minus 3 times the cube root. I think there's a cube root button, or you can go ahead and type it in like this to the 1/3 power. That's what I like to do, but I think there's a cube root on there. So I can type this in to get my decimal, and that is negative 0.24. So negative 0.24. So now from this, can I do my absolute max and min? I hope so. So who's the absolute smallest? It looks like it's going to be what? Negative 5. And negative 5 is my absolute min. Who is the absolute max? Who is the highest? Well, in this case, it looks like it's 0. So 0 is the big winner here. I'm going to have to shrink him down a little bit, make him fit. So that is my absolute maximum right there. Awesome. So you got to find all the points, and then you can figure out who the highest and the lowest is. Fantastic. We're going to wrap this up with some piecewise functions, just looking at graphs and see how we write these bad boys up here. So if I have just the picture of this, let's label everything on this. So when we're talking the extreme values, we're always talking the y values. So if I'm looking, I kind of go left to right on this. So is this an extreme value? Sure. We have what? All right, so we have an absolute minimum of what? What is the absolute minimum? We have an absolute minimum, and what is that value? The y value is 1. This is 1 high, so it's always the y value. Absolute minimum 1 when does this happen? When x is negative 3. So you have to write all this out. The extreme value and where they occur. So I've got an absolute min of 1 when x is negative 3. What else do I got? Here's another point right here. What is that bad boy up there? To me, that is the absolute max. That's the highest it gets. And that is an absolute max of what is that value up there? It looks like 5, isn't it? And when does that happen? That happens when x is 0. So the actual y value is the max or the min, and now I'm going to tell you where it happens. Do I have anything else? Sure, right here it looks like I have a local min. So I've got a local min. When does that happen? That happens when, or I'm sorry, the local min has a value of 2. And it happens when x is what? When x is 1. Open circle is nothing there. So that's how we got to write these up here. It's a little bit tedious. Got to write them up. Let's try the next one. So right here, I'm going to start with this. That looks like definitely the absolute lowest it ever gets. So we've got an absolute min to start. And what is that value? It's an absolute min of negative 5 when x is what? When x is negative 4. So we got to say when x is negative 4. Boom. Then the next point coming up would be here. That looks like the highest it gets. So we've got an absolute max. And what is that value? That is negative 1. And that happens when x is what? When x is -2, doesn't it? So -2 makes -1. That's that point right there. Excellent. Moving on. This is a critical point right here. It's pointy. It doesn't have a derivative, but is it a max or min? No, it's not. It's critical, but it's not doing anything. Here's my next max or min right here, and this is actually going to be a what? This is going to be a local. We got a local min, and this local min of what? That's -3. When x is what? We have when x is 3. Boom. Alright, so what do we got going on over here? Okay, so this is weird. We got this constant flat line. So what are constants? Constants are actually maximum and minimums. They're both. They're the high and the low. In this case, it's local. So we've got a local max slash min. This is really weird. Of what? It's going to be the maximum min of -2 when x is what? When x, and now we got to use some kind of interval notation because it's going to be between what? Between 3 and 4 inclusive there. So that's a constant. We're not going to worry too much about that, but in case it did come up, it's actually considered both of these. Awesome. Go ahead and let's pause the video. Try the next one. See how you do with that. Good luck. Alright, so here are the answers here. I actually typed these out so maybe you can read them a little bit better. Hopefully you got an absolute max of 3 at -1. You get an absolute min of -3 down here when x is 1. You've got a local max up here at 1 and a local min. So I kind of threw all 4 in there. That's it right there. If I give you piecewise algebraically, you'd have to kind of look at each breaking point and see from the left and the right who's higher. It's a little bit of work, but if you can think about the graph, it makes it a lot easier. So there it is. We're going to end with, instead of Extreme, I actually got Jack Black and Jimmy Fallon doing Extreme, and it's pretty awesome if you've seen the real video. Pretty hilarious. Good luck on this master check. Peace out.
Saying I love you is not the words I want to hear from you. It's not that I want you not to say it, but if you only knew how easy it would be to show me how you feel. More than words is all you have to do to make it real. And you wouldn't have to say that you love me, 'cause I'd already know. What would you do if my heart was torn in two? More than words to show you feel that you're